of homogeneous equation and non-homogeneous equation. So we need the definition first of all. That let capital A into X is equal to capital B be a system of linear equation, with small m equations and small n unknowns, then if capital B is equal to 0, then the system is called homogeneous, and if capital B is not equals to 0, then the system is called non-homogeneous. So here goes your definition of two different types of systems, one of which is called homogeneous and another is called non-homogeneous system. We are going to start discussing about the solving of these system of equations, and as a tool we are going to use rank row reduced or reduced row echelon form, independence of vectors, etc. Everything related to vector space so far discussed will be used as a tool to solve a system of homogeneous equation or system of non-homogeneous equation. Okay, and you have to remember this definition, that these are the conditions. If the right hand side is a vector, it's a column matrix, you can easily identify. If it is 0, if it is the 0 vector, then we shall call the system homogeneous. For example, you know the left hand side is this, on the left hand side capital A is the matrix. So we can consider the matrix as written in the following form. Okay, and small x is the vector, so we can consider how many vectors you are going to consider. Small n vectors you are going to consider. So we can multiply this row by that column, and consequently we can move on. And then we are going to equate the equation with the column vector 0, 0, 0. So that 0, 0, 0 is your capital B. Now, if capital B is 0, 0, 0, then that system is called homogeneous. That system is called homogeneous system. Okay. Now, on the other hand, if we have a system like this, and on the right hand side, I'm writing small b1, small b2, dot, 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 small bn, where bi's are not equal to 0 for all I, then that system is called non-homogeneous system. So this is the explicit representation of what has been written in the definition. Okay. So in the next paragraph, I'm next, and in the next page, I'm going to discuss about a theorem which gives you a technical tool of finding the solution of system of homogeneous equation, first of all. So let's discuss the theorem. I'm going to choose the theorem from the book, and I'm going to write its statement. The proof of the theorem is written in a very brief way. So I'm going to write it properly so that all of you can understand what it is actually saying. And also probably you can remember that when we talk about this type of system, Ax equal to b, that means we are actually talking about a linear transformation La, which is from Fn to Fm. Okay, so we have discussed this also. So actually capital A is equivalent to the linear transformation La. Okay, and that linear transformation La is defined as Ax. We have already discussed it earlier in module 4. Okay, sometimes when I get time, I shall try to connect this particular topic with vector space. So anyways, let's write the theorem, and the theorem says that let Ax is equal to 0 be a homogeneous system, of m linear equations and small n unknowns over a field capital F, over a field capital F. That means since we are considering a matrix capital A, the element of the matrix is chosen from the field capital F. And also, whenever you are going to find the solution for x, the value for x, so x is, it's x is a column vector. So it's also a kind of matrix, column matrix. Its elements are real. Its elements are chosen from field. So actually we will be dealing with a real system of homogeneous equation. Okay, because set of real number is a field. Let capital K denote the set of all solutions, to Ax equal to 0. Here this 0 is actually the 0 vector. So it would be nice if I put 0 bar. This is not a scalar 0 they are talking about. Okay, then capital K is equal to n into La. Hence K is a subspace. K is a subspace of Fn of dimension small n is equal, small n minus rank of La is equal to n minus rank of A. Okay, and you have to put it inside a box because that is the formula which we'll be using to solve system of homogeneous equation. And this theorem also has a corollary. The corollary says if m less than n, the system Ax equal to 0 bar has a non-zero solution, All these terms written over here are familiar to you. Nothing new has been interpreted, but I have to discuss a bit of these things for your proper understanding. I have talked up to this. Now you see, do not think that Sir is always trying to drag us into the domain of vector space or linear algebra. I'm not doing it intentionally because we are actually learning a subject which is connected to that, and it wouldn't be fair if I do not show you the connection between the current topic and the earlier discussed one. Okay, so I'm not doing it intentionally, but the situation is making me do it again and again for your proper understanding. Now, you already know that LA is the linear transformation from Fn to Fm. Okay, and this LA is defined as AX. In one of the chapters, we have learned this. What is N of LA? N of LA is actually nullity of the linear transformation, nullity of LA. What is nullity of LA? Nullity means dimension of kernel of LA. Okay, so that is the definition I'm reminding you. Now they have defined K to be the set of all solutions to the system AX equal to 0 bar. So how K becomes N of LA? So let me show this to you. Now, by definition, capital K contains set of contains all the solutions of the given system AX equal to 0. So it contains all such vectors small s belonging to the vector space Fn such that AS equal to 0 bar. And if you can recall the definition of kernel, so kernel's definition, try to look at the kernel's definition, which is defined in the chapter of linear transformation. The definition is exactly like this. We are interested about those vectors. If you have forgotten, kernel of the linear transformation means we are interested about those vectors of the vector space V such that T of X equal to 0 bar. 0 bar is the 0 vector. Okay, so try to connect this definition with the given one. So definitely, since the associate linear transformation is LA, so we can write this as set of all vectors of the vector space Fn so that LA of S is equal to 0 bar. Okay, and therefore this K is actually what? This K is actually kernel of LA. This K is actually kernel of LA, and not kernel of LA actually. Actually, we have defined this K to be the set of all solutions. So how many solutions are there in K? That is important for us. How many vectors are there? So in K, that is important for us, and therefore dimension of K is actually dimension of kernel of LA. Okay, and that is the thing which we are supposed to find. Dimension of K, which is dimension of kernel of LA. Okay, now that we can write it as dimension of kernel of LA means null space or nullity of kernel of LA. Okay, and we can call it not nullity of kernel of LA, sorry. Dimension of kernel of LA is actually nullity of LA, and we can call it as N of LA. Okay, so dimension of K, here actually some printing mistake is there. That should be dimension of K. That should be dimension of K. Okay, so that is the thing. Now we know that since probably you can recall there was a definition which there is a theorem which goes like that. it said nullity of T plus rank of T is equal to dimension of V. This theorem is called the dimension theorem. Okay. Now you see this, since LA is equivalent to the matrix capital A, therefore rank of LA will be same as rank of the matrix capital A. Okay. So if you can find the rank of A, then we will be actually able to find rank of LA. Now, if we can find rank of LA by using this particular theorem, we can write n of LA plus rank of LA is equal to dimension of Fn, because here my T is LA, my vector space V is Fn, and we know that this can be written as n of LA is equal to dimension of Fn minus rank of LA. Okay, so from this analysis, we can easily write n of LA to be dimension of Fn. Dimension of Fn means n, and LA is same as capital A, equivalent, their characteristics are same. I mean, they are characteristically same. So in place of LA, we can write rank of A only. Okay, and therefore we have got our, let me write it properly, rank of A, because LA and A are equivalent, and we have got this particular result, which is very important. This particular result, which is very important. So n of LA means it contains all such elements which are the solutions, all such elements which are the solutions of the system. So if you can, how many solutions are there, that is the nullity, and you can find the number of solutions satisfying the equation Ax equal to 0 bar by the formula this. So we have the matrix capital A with us. So let's find rank. We already know how to find rank. And once you find rank, rank is a number, we can subtract rank from the total number of unknowns, n, which is actually dimension of Fn. So that will give you the number of solutions present in this particular set capital K. So this is your formula. So what is the formula? That is your formula. So this is all about the theorem. Okay, so let's talk about the corollary. Corollary is very important. The corollary says that if m less than n, the system Ax equal to 0 has a non-zero solution. If k is, what is m? M is number of equation, n is number of unknowns. Okay, so according to the corollary, it is written that suppose m is less than n. What is m? M is number of equations and n is number of unknowns. Number of unknowns. Okay, so if this is so, then we know that the rank of A, rank of the matrix capital A, which is equal to rank of LA, since A and LA are same, so that should be either equal to m or less than m. Suppose rank of A is equal to R. Okay, so that a number R either is equal to the number of equation or will be less than that. Hence, in that case, dimension of K will be equal to n minus rank of LA, which is equal to n minus rank of A, which is greater than or equal to n minus m. How? Since rank of LA is less than or equal to m, according to our assumption, so minus rank of LA should be greater than or equal to minus m, this implies n minus rank of LA should be greater than or equal to n minus m, and that is n minus rank of A should be greater than or equal to n minus m. And according to our assumption, m is less than n, so this n minus m is greater than 0. So dimension k, what do we get here? We get dimension of k is actually greater than 0, and therefore k is not equal to the 0 vector. I mean, solution is not the 0 solution only. Since k is strictly, dimension of k is strictly positive, thus there exists a non-zero vector S prime belonging to capital K such that S prime is the non-zero solution of the system, of the homogeneous system Ax equal to 0 bar. Okay. So this is the condition you have to keep in mind. This is the condition you have to keep in mind. And you see, when we consider Ax equal to 0 bar, and if you ask me what about this particular vector, if I put x equal to 0 0 0, and if I multiply A by this vector, if we choose this, I will say, okay, you are right, this solution is called trivial solution. This is called trivial solution. Okay. And here, if m less than n, then that solution is called non-trivial solution. So we are actually considering here the non-trivial case, non-trivial solution. So this is the condition under which the system will be having non-trivial solution. Okay. So I hope you have understood. Let's discuss one particular problem. Example, we considered the following system. We consider the following system of equations x1 plus 2x2 plus x3 is equal to 0, x1 minus x2 minus x3 is equal to 0. So we are going to find whether this system has a trivial solution or non-trivial solution. Obviously, this system is non-homogeneous. Try to correlate with this system, the given system, with Ax equal to 0. And if I compare this system with Ax equal to 0, we see that capital A, the coefficient matrix here is 1, 2, 1, 1, minus 1, minus 1. Okay. So, and here the number of unknowns is equal to 3. Okay. So our job is to find rank of A. So let's do it. Let's do it by our usual process. Now, regarding finding rank, and as you have come to know about reduced row echelon matrix, there is a trick I must tell you, because each time we try to solve a solution, to solve a system, we shall be discussing to find rank. So rank is the ultimate tool over in this particular chapter. So trick is, forget what was written in the reduced row echelon matrix strategies. Okay, so forget about that. Your job is to bring, and I'm not, this particular line which I'm writing over here, it's my line. I'm writing it. I'm not taking it in from any book. So it is just a pedagogical point of view. It's just a trick to help you out. Try to bring the matrix identical to or equal to identity. That is the trick. If you do so, or if you can at least do so, then you will be actually dealing with reduced row echelon matrix. So here, if I keep this trick in mind, so to find rank, what I will do, I will keep the first row fixed. So R1 will remain fixed. Okay, and R2 can be changed as R2 minus R1, which is 1 minus 1 0, minus 1 minus 2, that is minus 3, and minus 1 minus 1, that is minus 2. Okay, and that, since I'm dealing with a rectangular matrix, so that will not be a perfect identity. So that's why I have written here identical to identity matrix, or maybe it is equal to identity in case of square matrix. So that is the thing what I can do at least further. So I can bring 1 over here by dividing this matrix, this particular row, by minus 3. Okay, so we'll be getting 1 and minus 2 by 3. Okay, that much we can do. And if you want to do further, so we can at least do what? We can multiply R2 by 2, and we can subtract 2R1, sorry, 2R2 from R1. R1 minus 2R2. So what do we get? 2 into 0, that is 0. So 1 minus 0, that is 1. 2 into 2, that is 2. 2 minus 2, that is 0. And 2 into 2, that is 4, minus 4 by 3. So 1 minus 4 by 3. So 1 minus 4 by 3. So we can write it as that is equal to 1 plus 4 by 3. So that is 7 by 3. And 0 1. Someone has raised his hand. So yes, tell me. Tell me what you want to say. Have I done any mistake? Dheeraj, you can unmute yourself and tell me.
Sir, when we are changing R2 to R2 by minus 3, the last element will become 2 by 3, right?
Yes, 2 by 3 plus. Mistake, my mistake. It's not minus 2 by 3 because we are dividing by minus 3. Okay, now so that I must correct it. Thank you, Dheeraj. So that would be 4 by 3, 1 minus 4 by 3. 1 minus 4 by 3 means minus 4 by 3 means minus 1 by 3. Okay, so that is minus 1 by 3, and this is 2 by 3. So you cannot reduce. This is not an identical this is not identical to identity. I mean, this is identical to identity to some extent, but it's not exactly identity because it is a rectangular matrix. But if you look at this particular matrix properly, you will see that this satisfies every criteria defined in reduced row echelon form. So every criteria which is defined over here, it is being satisfied here. So you can say that, yeah, I have done the reduced row operation. But keep in mind, when we'll be dealing with a system of equation, we shall try to use always the row operations and not column operations. There are some reasons for doing this. Anyways, so ultimately after this operation, we have got the rank of A to be equal to 2. and that is equal to that is equal to then that is equal to actually the number of equations which is your m, and it is less than number of unknowns, which is your n, which is 3 over here. So by the formula we have just defined dimension of K will be n minus rank of A, and therefore we can write 3 minus 2 equal to 1. And what does this mean? If you can recall the property of the meaning of dimension, dimension gives you number of linearly independent vectors. So how many vectors are there in this particular case? Actually, we have 3 vectors, x1, x2, x3. 3 elements consisting of one vector, x1, x2, x3. And out of this, we have this. So out of these 3 elements, one can be chosen, one element can be given independent choice, This one element can be either x1 or x2 or x3, as you wish. Okay, so there is no restriction on which element to select. This is our choice. We can select any one of these 3, but we have to, only one will become independent because of this. Now, without any loss of generality, this statement in mathematics is very important. Without any loss of generality, that means we have many general choices. We could have selected x1 to be independent, we could have selected x2 to be independent, we could have selected x3 to be independent. So keeping that generality in mind, let x3 be the independent choice, x3 be the independent variable. If you don't want to go according to my choice, you can go with your own choice. X3 be the independent variable, and let x3 equal to k, sorry, not k, p. P is real. Why? Because we are choosing everything from the field capital F. We already defined in the theorem. Now, therefore, the system can be written as the system. Time is running out, so I'm enabling the chat box so that you can put your attendance quickly. You can do it. So the system now becomes x1 plus 2x2 is equal to minus x3, which is minus p, and x1 minus x2, which is x3, which is equal to capital P. And if you, and now we have, since we have got this particular system, okay, so we will try to write its augmented form now. We will try to write the augmented form, the augmented matrix, to solve it. The given matrix can be represented in the following way. We can write it as 1, 2, 1, minus 1. This multiplied by x1, x2, and which is minus p and plus p. Okay, these are constants actually. And corresponding to that, the augmented matrix will be of the form 1, 2, 1, minus 1, p, minus p, and plus p. And this can be actually written as 1, 2, minus p, which is where R1 is remaining same, and we are writing where R2 is actually R2 minus R1. And this can be further written as 1, 2, 0, 1, minus p minus 2p by 3, where R2 is divided by R2 minus R2 by minus 3 as before. And this can be further written as 1001 p by 3 minus 2p by 3. Let's do up to this. We shall continue in the next session.